Hello students, welcome back. In section 1, we went through the theory of linear functions. Now let's do some applications. Let's look at some linear models. Remember, the average rate of change is the slope, and the slope should be constant everywhere for linear functions, alright? And remember that for this example problem. Stop the playback and read through the problems. So what do we have here? A strain of E. coli known as both 397 Rec A441 is placed into a petri dish at 30 degrees Celsius and allowed to grow. The data shown in table 2 are collected. The population measured in grams and the time in hours. Plot the ordered pairs x, y in Cartesian plane and use the average rate of change to determine whether the function is linear. And the idea is to use average rate of change. But then again, in order to do anything, we have to have the data table. And okay, here's the data table. What you can do is stop the playback and plot this on graph paper, but of course that's going to be a bit cumbersome, so I'm going to provide it here, and here we go. There you go. Now, use inspection. Does it look like linear? It doesn't look very linear to me. You see, if you look at the average rate of change, that is slope, in interval 0 to 1 and interval 1 to 2, 2 to 3, 3 to 4, 4 to 5, looks like they're different. Especially this one, 4 to 5 versus 0 to 1, looks like this one is stiffer, this one flatter. You can use technology to find out the line of best fit or the regression line, and then you get something like this. I don't know, does it look okay to you? To a certain degree it is okay if you just force it in, but I'm not really comfortable. It doesn't really look linear, but then again, let's check, really check. Let's find out the average rate of change. First interval, change of y coordinate over change of x coordinate. Second interval, change of y coordinate over change of x coordinate. Change of y coordinate over change of x coordinate. So difference here, 0.29 minus 0.22 over 4 minus 5. Difference of these two, 0.39 minus 0.29 over 5 minus 4. You see, that's how I find out the average rate of change for each interval. If you do your computation, let's see, font is too light. Yeah, if you do your computation, it turns out in the first interval from 0 to 1, 0.12 minus 0.09 over 1 minus 0. 0.03 is the average rate of change. In the second interval, if you do your computation and punch in the calculator, you get different number. And let's go to the last interval. Very different from the first. As a matter of fact, excuse me, it will be better with bigger font. Or, maybe not, it's just... Okay, we have a bunch of fractions, so bigger font will be helpful. Okay, what do we have here? Difference of y coordinate over difference of x coordinate. Difference of y coordinate over difference of x coordinate. Calculate all those from this table. Brute force method, and then punch in the calculator. Do you have the same slope? Not really, they are very different. So what's the conclusion? This is not a linear model. Let's see. Oh, let me go back to original size. So if you join those, then you get much flatter line, much stiffer line. As a matter of fact, it'll turn out this is an exponential model. So we have this kind of curve. But then again, we're going to deal with the exponential function in, let's see, is it going to be week 10 or so? I'm not so sure. in the latter half of the course sometime, so we are not ready yet. So at this moment, let's just conclude this is nonlinear. How about the next problem here? Data table 3, and here we go. Maximum number of heartbeats that a healthy individual of different ages should have 15-second interval of time while exercising, plot the ordered pairs, and so on and so forth. And then we have ages 20, 30, 40, 50, 60, and 70 as X, and then heartbeats. Now, find out the average rate of change, that is, difference of y-coordinate over difference of x-coordinate. Difference of y-coordinate, difference of x-coordinate, like this. That is, 47.5 minus 50 over 30 minus 20, kind of like that. 40 minus 42.5 over 60 minus 50, like those. Change of y over change of x. If you do all those, what do you get? Let's see. First, the graph. Does it look linear? Yes, it does. If you use technology, you can find the line of best fit. Oh, it's very linear. Now, let's make sure. What is the average rate of change at each interval? Let me expand the font. First interval, nearly 0.25. Second interval, third interval, fourth interval, they're all the same. So what do we have? We have the slope of negative 0.25 or negative 1/4. And then we have linear model. Okay, that concludes example 2.2. How about the next problem? Okay, all right. Two linear models put together. The quantity supplied of a good is the amount of a product that a company is willing to make available for sale at given price. The quantity of demand of a good is the amount of product that consumers are willing to purchase at a given price P. Suppose that the quantity supplied S and the quantity demanded D of smartphones each month are given by the following functions. All right, 15p minus 900 versus negative 3.75p plus 2850. All right, that's not the end of the problem. It's just a background information. What do we have to do? Okay, the equilibrium price of a product is defined as the price at which the quantity quantity supplied equals quantity demanded. So okay, these two must be equal. Find the equilibrium price of smartphones. And what is the equilibrium quantity? Okay, set these equal and find out price P. And then at that point, the quantity S of P or D of P, they are going to be the same anyway. Make sense? And then determine the prices for which quantity of supplied is greater than quantity of demand. So S of P is greater, so you have to solve an inequality. Okay, all right, let's see. Graph this, graph that, and then you can do those with graphing calculator. Assuming you did, you get this graph. So blue is supply and red is demand, like this. And then crossing point right here around P of 200, D and S meet. So that's gotta be the equilibrium. Make sense? You see, equilibrium should have the same, these two have to be the same. S is blue and D is red. And then they meet, they are equal right here. So set these two equal. 15p minus 900 equal to negative 3.75p plus 2850. Set those equal and then solve for p. So this is price, blue, and this is demand, red. And then solving this equation, I'll leave you there. I have some decimals, but it's not too bad. Flip this one over to the other side, 15 plus 3.75, so 1875p. Flip this one over to the other side, 3750, and finally divide this one away, punch it to the calculator, you get about 200. It looks like really 200. So that's a price, equilibrium price. Now if you want to find that equilibrium quantity, you can have to plug it into any function. We have two linear functions, S of p or d of p. Which one do you choose? It doesn't matter because they're going to be the same there anyway. What did I do here? Did I select? I didn't bother selecting that, as a matter of fact. And if student does this way, then the student will lose some credit. Sorry about this. So S of 200, I just select this to do with supply P. So 15P, so 200 minus 900, you see, 15P minus 900, P is 200. So that computation yields, well, punch in the calculator. I'll punch this into the calculator. 2100. And that's the equilibrium quantity in this case. Now, what if you used demand function? Plug in 200 over here, and are you going to get the same 2100 as well? Yes. If not, something is wrong. You either made some mistake solving an equation or doing a computation, something. They should be the same. Okay, so much for part A, and part B. Yeah, S is greater than D, so blue is S, red is D, and blue should be greater. So looking at this, to the right, price is greater than 200. That's when blue is greater, supply is greater. You can set up equation. This is blue, and that's red, and then do exactly the same thing, except that this time it is inequality, and then divide by 18.75, which is positive number, so P is greater than 200. Next, we have some piecewise linear models, but running out of time. So let's stop here, and then we're going to do next examples in separate videos. Maybe one more, maybe two more.